Complete solutions for the approximate synthesis of spherical 4-bar function generators. The spherical 4-bar is a 1 degree of freedom mechanism with 4 links and 4 joints, whose axes intersect at a single point. Its kinematic design can be modeled by 4 vectors represented in a reference configuration. The goal of function generation is to synthesize a mechanism that coordinates the rotation of the input link phi with the rotation of the output link psi. We specify a number of angle pairs phi psi and solve for the design variables SB0, SC0, and SD0. Without loss of generality, we specify SA0 to be in the 1, 0, 0 direction. Our aim is to compute the complete solution set for exact and approximate cases of spherical 4-bar function generation. Local solvers can be effective for design tuning when a reasonable starting point is known. However, a complete solution set is superior for design exploration, where areas of interest can be found globally across the design space. In this paper, we review the synthesis solutions for 2 exact cases, and more novelly, contribute complete solution sets to 2 approximate cases of spherical 4-bar synthesis. In approximate synthesis, a mechanism is designed to approximate any number of angle pairs. We formulate and solve the case where the ground pivot SB0 is specified, which has 61 finite isolated solutions, and the general case where SB0 remains unknown. 268 finite isolated solutions were computed for this case using the random monodromy loops technique. In this video, we illustrate the first approximate case. The objective of this optimization problem is to solve for the vectors SC0 and SD0 that minimize the error to which a fixed angle constraint is met. An additional variable, RCD, is introduced, which is a dot product defined from a best fit coupler angle. This problem is subject to 2 sphere constraints, which specify unit magnitude for SC0 and SD0. With the optimization problem formulated, the Lagrangian can be constructed by introducing lambda, a vector of Lagrange multipliers. The partial derivatives form a system of 9 polynomials and 9 unknowns. The roots of this system indicate the critical points of the optimization problem. The Bézier degree of the system is 3,564, indicating up to that many critical points exist. Task data can be collected into the coefficients of our polynomial stationarity conditions as large summations of symmetric matrices that may be evaluated before the numerical solution process begins. By increasing the number of discretization points, these coefficient summations form a sort of signature for any continuous curve in phi psi space. We applied the homotopic continuation solver Bertini, which tracked 3,564 paths and found 244 finite isolated solutions. Due to the sphere constraints, solutions appeared in redundant sets of 4, allowing a reduction down to a maximum of 61 critical points. This procedure was implemented in an interactive design tool. Here, the angle pairs for a desired function are dragged into place by a user. The interface calls Bertini to find the 61 critical points. The real physical solutions are displayed for easy analysis and selection. The user can visualize and interact with the mechanisms synthesized by each solution. We applied this algorithm to a novel folding wing design. In this design, aircraft wings unfold from a stowed configuration via intersecting spatial joints. Due to the overlapping tabs of the wings, the timing of their deployment is critical. When the left wing, shown here in blue, deploys more quickly than the right wing, shown in green, the 2 wings collide, resulting in a failed deployment. A collision would also occur if the wing coordination was linear, as produced by bevel gears. To coordinate these wings in a nonlinear manner with no collisions, a spherical function generator was implemented. The pivots SA0 and SB0 were specified from the axes of the existing joints, and 10 angle pairs were chosen. The synthesis procedure resulted in 12 real non-degenerate solutions, including 3 minima. Solution 2, a minimum, best approximated the angle pairs, so it was chosen. The function generator was implemented in the folding wing design and prototyped, as shown here. By rotating the right wing, the left wing is able to swing into place without any possibility of collision. Thank you.